There isn't another article in the National Electrical Code that mandates grounding a 480-volt primary to 120-volt secondary 50-volt ampere transformer specifically within a control panel. Article 270.170 addresses secondary circuit grounding when the primary voltage exceeds 300 volts to ground. However, this doesn't automatically apply to all 480-volt to 120-volt transformers. Grounding for troubleshooting purposes, while a common practice, isn't necessarily a code requirement in this specific scenario. The necessity for grounding hinges on several factors, including the transformer's application and the characteristics of the secondary circuit. Let's delve into the technical aspects. Firstly, the National Electrical Code, or NEC, outlines general grounding requirements in Article 250. It's crucial to consult this article to determine if grounding is required based on the specific circumstances. Secondly, consider the transformer's role in the overall system. Is it supplying power to lighting, receptacles, or control circuits? The type of load connected to the secondary side can influence the need for grounding. Thirdly, the voltage level of the secondary circuit is a key factor. Circuits operating at 50 volts or more are typically required to be grounded unless specific exceptions apply. Understanding the NEC grounding philosophy is paramount. Grounding serves several critical functions, including limiting voltage surges, stabilizing voltage to ground, and providing a low impedance path for fault current to facilitate overcurrent device operation. In a control panel setting, transformers are often used to step down voltage for control circuits. While not always mandated, grounding the secondary side of a transformer can enhance safety and improve system performance. When dealing with transformers, it's essential to differentiate between system grounding and equipment grounding. System grounding refers to connecting the neutral point of a power system to ground, while equipment grounding involves connecting non-current carrying metal parts of electrical equipment to ground. The equipment grounding conductor provides a path for fault current to return to the source, thereby tripping a circuit breaker or blowing a fuse. Now, let's explore some of the relevant NEC sections that might influence the decision to ground the secondary of a 480-volt to 120-volt transformer. NEC Section 250.20 addresses systems to be grounded. It stipulates that alternating current systems of 50 volts to 1000 volts that supply premises wiring systems must be grounded under certain conditions. These conditions include when the system can be grounded such that the maximum voltage to ground on the ungrounded conductors does not exceed 150 volts, and when the system is a three-phase, four-wire Y-connected system in which the neutral is used as a circuit conductor. Another relevant section is NEC Section 250.21, which outlines systems not required to be grounded. This section provides exceptions to the general rule requiring grounding. For example, an isolated power system used in healthcare facilities is typically not grounded to minimize the risk of electric shock. Furthermore, NEC Section 450, which covers transformers, provides specific requirements for transformer installations. This section addresses issues such as overcurrent protection, guarding, and ventilation. While it doesn't explicitly mandate grounding in all cases, it's essential to comply with the requirements outlined in this section. In the context of a 480-volt to 120-volt transformer in a control panel, it's crucial to consider the following factors before deciding whether to ground the secondary side. Firstly, the voltage level of the secondary circuit. Since the secondary voltage is 120 volts, it falls within the range where grounding is typically required. Secondly, the type of load connected to the secondary circuit. If the load is sensitive to voltage fluctuations or requires a stable reference to ground, grounding the secondary side may be beneficial. Thirdly, the presence of other grounded systems in the vicinity. If other systems in the control panel are grounded, it may be advantageous to ground the transformer secondary to maintain a consistent ground reference. Fourthly, local codes and regulations. Some jurisdictions may have specific requirements for grounding transformers that go beyond the NEC requirements. Now, let's discuss the practical aspects of grounding a transformer secondary. The grounding conductor should be sized in accordance with NEC Table 250.122. This table provides guidance on selecting the appropriate grounding conductor size based on the size of the overcurrent protective device protecting the circuit. The grounding conductor should be connected to a suitable grounding electrode, such as a grounding rod, a metal water pipe, or building steel structure. The grounding electrode should be installed in accordance with NEC Section 250.52. It's also important to ensure that the grounding connections are mechanically and electrically sound. Loose or corroded connections can compromise the effectiveness of the grounding system. In addition to system grounding, equipment grounding is also crucial for safety. All non-current carrying metal parts of the transformer and the control panel should be properly grounded. This includes the transformer enclosure, the control panel enclosure, and any other metal components that could become energized in the event of a fault. The equipment grounding conductor should be sized in accordance with NEC Table 250.122 and connected to a suitable grounding electrode. Proper grounding practices can significantly reduce the risk of electric shock and equipment damage. It's also worth noting that some control panel manufacturers may have specific recommendations for grounding transformers in their equipment. Always consult the manufacturer's instructions and follow their recommendations. In summary, while the NEC doesn't explicitly mandate grounding a 480-volt primary to 120-volt secondary 50-volt ampere transformer in a control panel in every situation, it's essential to consider the factors outlined above and comply with all applicable codes and regulations. Grounding can enhance safety, improve system performance, and provide a more reliable electrical system. Always consult with a qualified electrician or electrical engineer to determine the appropriate grounding strategy for a specific application. Let's further examine the implications of not grounding the secondary side of a 480-volt to 120-volt transformer. In the absence of a ground connection, the secondary circuit can float at an undefined voltage potential with respect to ground. This can lead to several potential problems. Firstly, it can increase the risk of electric shock. If a person comes into contact with an ungrounded conductor, the voltage difference between the conductor and ground may be high enough to cause a dangerous shock. Secondly, it can make it difficult to troubleshoot electrical problems. Without a stable ground reference, it can be challenging to identify the source of faults or voltage fluctuations. Thirdly, it can increase the susceptibility of the equipment to voltage surges and transients. A grounded system provides a path for these surges to dissipate, protecting sensitive electronic components from damage. Furthermore, consider the impact on the overcurrent protection system. In a grounded system, a ground fault will typically result in a high fault current that will quickly trip a circuit breaker or blow a fuse. However, in an ungrounded system, a ground fault may not draw enough current to trip the overcurrent device, leaving the fault condition unaddressed. This can create a hazardous situation and potentially lead to equipment damage or fire. Now, let's discuss some of the common misconceptions about grounding transformers. One common misconception is that grounding is only necessary for high-voltage systems. In reality, grounding is important for systems of all voltage levels, including low-voltage systems like 120-volt circuits. Another misconception is that grounding is only required for systems that supply power to lighting or receptacles. Grounding is also important for systems that supply power to control circuits, electronic equipment, and other types of loads. It is imperative to remember that the primary purpose of grounding is safety. A properly grounded system provides a safe and reliable electrical environment for personnel and equipment. When in doubt, it is always best to err on the side of caution and ground the secondary side of a transformer. Furthermore, keep in mind that the NEC is a minimum standard. Some organizations and industries may have more stringent grounding requirements. For example, healthcare facilities, industrial plants, and data centers often have specific grounding requirements that go beyond the NEC requirements. These additional requirements are typically designed to address the unique electrical safety needs of these environments. When working with electrical systems, it's essential to stay up to date on the latest codes and regulations. The NEC is updated every 3 years, and significant changes can occur from one edition to the next. It's also important to be aware of any local amendments or interpretations of the NEC. These amendments can vary from jurisdiction to jurisdiction and may impact the grounding requirements in a specific area. In addition to the NEC, other standards and guidelines may provide valuable information on grounding practices. For example, the Institute of Electrical and Electronics Engineers, or IEE, publishes numerous standards on grounding and bonding. These standards provide detailed guidance on designing and installing grounding systems for various types of equipment and facilities. Furthermore, many manufacturers of electrical equipment provide detailed instructions on grounding their products. These instructions should be carefully followed to ensure proper grounding and safe operation. In conclusion, grounding a 480-volt primary to 120-volt secondary transformer is a multifaceted issue that requires careful consideration of various factors. While the NEC doesn't mandate grounding in every situation, it's essential to evaluate the specific application and comply with all applicable codes and regulations. Grounding can enhance safety, improve system performance, and provide a more reliable electrical system. Always consult with a qualified electrician or electrical engineer to determine the appropriate grounding strategy for a specific application and to ensure compliance with all applicable requirements. Also remember to consider the specific equipment that is used and follow the manufacturer's recommendations. When grounding, use the appropriate tools and materials. Use a properly sized grounding conductor, appropriate connectors, and a suitable grounding electrode. Ensure that all connections are mechanically and electrically sound. Loose or corroded connections can compromise the effectiveness of the grounding system and create a safety hazard. Finally, remember that electrical work can be dangerous. Always take appropriate safety precautions when working with electrical systems. Wear appropriate personal protective equipment such as safety glasses, gloves, and insulated tools to energize the circuit before working on it whenever possible. If you are not qualified to perform electrical work, hire a licensed electrician to do the job. Understanding the nuances of grounding, especially with transformers, is essential for electrical safety and system reliability. While a specific NEC article may not explicitly demand grounding in every 480-volt to 120-volt transformer scenario within a control panel, the cumulative effect of various code sections, best practices, and safety considerations often leads to the conclusion that grounding is the most prudent approach.